Hi everyone, today a video in the bonding and structure topic looking at shapes of molecules and ions. So molecules are three-dimensional. Even though on the paper we typically draw them just down in 2 dimensions, we have to remember that in the real world they exist as three-dimensional shapes. And we know that electrons exist in pairs in volumes of space that we call orbitals. We have this idea of our electron density, our electron clouds, rather than just discrete particles. And we can predict the shape of a simple covalent molecule by using the ideas that each pair of electrons around an atom will repel all other electron pairs. That's just electrostatic repulsion. Negatively charged things don't want to be near to each other, they repel. And the pairs of electrons will therefore take up positions as far apart as possible from each other to minimise the repulsion. So they want to get physically as far away from each other as they can do. And this is called the valence shell electron pair repulsion theory, or VSEPR. Now, electrons may be in a shared pair in a covalent bond, or they could be in a non-bonding lone pair. And the shape of a simple molecule depends on the number of pairs of electrons that surround the central atom. And so to work out the shape of a molecule, we have to count how many electrons there are. And the order of repulsion is as follows. Lone pair repulsions are the strongest, then lone pair bonding pair repulsions, and then finally bonding pair repulsions. So lone pairs repel more than bonding pairs do. Now, as I said, to work out the shape of a molecule, we have to count our electrons. So we're going to work out the total amount of bonding electrons, so how many electrons we have. We're going to divide by 2 because electrons are in pairs. Then we're going to look and see, well, how many of those electron pairs are actually used in covalent bonds? How many of them are lone pairs? And the way to do it really is to count the central atom first. So in any sort of shape, there'll be one atom that is at the centre of our molecule, and we include all the valence electrons. So if our central atom is carbon, carbon's in group 4, so it has 4 valence electrons. If our central atom is nitrogen, nitrogen's in group 5, it has 5 valence electrons, and so forth. Then we count any other atoms, and if it's not the central atom, a slightly sort of cheap way to do it is to only count the electrons that are donated by that atom to form a covalent bond. So for example, if I have a carbon-hydrogen bond, I know that I've got 1 electron from my carbon and 1 electron from the hydrogen. If I, for example, have a carbon-fluorine bond, I know that I've got 1 electron from the carbon and 1 electron from the fluorine. Now, rather than counting the fluorine as having 7 electrons, I'm actually only going to say it has 1, because all I'm interested in is the electrons that are used in the bond. For the central atom, I'm interested in all of its electrons, the valence electrons, whether they're bonding or lone pair electrons. But for the atoms that surround it, all I'm interested in is just what the bonding electrons are. So for the fluorine, rather than thinking of it as 3 lone pairs and 1 bonding electron shared in the covalent bond, I can just think of it as just the electron that's donated from that atom to form a covalent bond. And another example, if I have an oxygen bonded to a central atom, typically an oxygen uses 2 electrons. We think of oxygen typically having double bonds to things. So let's start to look at some of the shapes. If we have 2 pairs of electrons around a central atom, the molecule will be linear, because the furthest away the 2 electron pairs can get is if they are 180 degrees away from each other, literally on opposite ends of that central atom. So the key thing is, remember, going back to the VSEPR theory, that our electron pairs want to get physically as far away from each other as possible. And so in this linear system, where we only have 2 electron pairs around our central atom, it's a linear molecule and we have 180 degrees between our electron pairs. Now, an example of this would be beryllium chloride. So if we're going to work out the shape of this, the first thing we do is check our central atom. The central atom is the beryllium in this case. We then think about how many electrons beryllium has. Beryllium's in group 2, so it has 2 electrons. We're then going to think about the chlorine, and here I'm showing it as counting all the electrons. So you can either count all the electrons or do the sort of cheap method I said on the previous slide of only counting the electrons in covalent bonds. Here I'm going to show you how to do it the full way. So chlorine is in group 7. It has 7 electrons. We have 2 of them. So therefore in total we end up with 14 electrons from the chlorine. And if we add the 14 from the chlorine and the 2 from the beryllium, we end up with 16 electrons. Remember that electrons are always in pairs, so we divide by 2, and that means we have 8 electron pairs. And so if we then put these pairs around our atom, beryllium had 2 electrons. It's therefore going to share, it's going to have one of these sharing with one of them from the chlorine, so we can put 4 electrons around our beryllium, that's 2 pairs. And then we are therefore left with 6 pairs, and we can put 3 on each of the chlorines to give those an octet, the 8 electrons. And our beryllium actually only has 4 valence electrons. That's something we'll come back to in just a second. The alternative method, the method of just counting the electrons that are used in covalent bonds, remember that the central atom we always count all the electrons for, so beryllium being in group 2, 2 electrons. Our chlorine is in group 7, so it actually uses 1 electron in a covalent bond. And so we can think of the chlorines as actually sharing 1 electron each, and therefore we have 2 electrons from the chlorine. So 2 electrons from the beryllium, 2 from the chlorines gives us 4, divided by 2 gives us 2 pairs of electrons, and therefore we have 2 pairs of electrons around our central atom, and that's what we see, 2 pairs of electrons on the beryllium atom. And so the way that this works by only considering the electrons that are being donated from the other atoms, so 1 for chlorine for example, is that we're only interested then on the electron pairs on the central atom. We're not interested about the electrons that go on the outer atoms, so in this case all the 3 other lone pairs on the chlorine. So using this sort of cheat method is just a way to kind of simplify down the diagram, simplify down the numbers, and often it's a better way because there's a less chance of making mistakes. Now you can see here that beryllium only has 4 valence electrons. It's very electron deficient. We know that things like to have that stable noble gas configuration of 8 electrons in their outer shell. And so actually, as you see in this sort of diagram here in the middle, beryllium actually exists, this beryllium dichloride actually exists as this kind of almost like polymeric chain. So what we have here is, if we look at the beryllium directly in the centre here, we have our beryllium dichloride, our linear molecule, and then you can see we have 2 arrows. These represent dative covalent bonds. So remember, a dative covalent bond is where we have both atoms being donated from both electrons being donated from 1 atom rather than a 1-on-1 shared covalent bond. And so we have 2 dative bonds from these chlorines on either side because these have lone pairs, and therefore we end up with beryllium then having 8 valence electrons. So it doesn't actually exist really as this monomeric state, it exists as this kind of polymeric sort of chain state. Now if there are 3 pairs of electrons around the central atom, think about a triangle having 360 degrees, divide it by 3. The angle between these bonds will be 120 degrees. So these electron pairs go 120 degrees apart, and the molecule is flat, it's planar, and the shape is called trigonal planar. Literally, it's based off a triangle, it's planar, so it's trigonal plane. And an example would be BF3. So again, we can think of boron, our central atom here, in group 3, so it has 3 electrons. We could either think of the fluorines as having 7 electrons, and we have 3 of them, so therefore we have 21 electrons, and so the total is 24 electrons, or 12 pairs. Or we can think about it in the cheat method of having the the boron having 3 electrons. The fluorines are each going to donate 1 electron in the covalent bonds. So we have 3 lots of 1 from the fluorines to give us 3 electrons. That's a total of 6 electrons, and therefore 3 pairs. So if we use the 3 pairs of electrons, that just means we have 3 pairs of electrons around our boron. If we're using the total number of electron pairs, well, we then end up having 12 pairs of electrons. So we're going to put 3 around our boron. We know that boron has 3 electrons to start with. It accepts 1, essentially shares 1 from each of the fluorines. So in those shared covalent bonds there, we have 3 from the fluorines, so we end up with 6 around the boron. And then we can use up all of our other pairs by just making sure that each of the fluorines has 8 valence electrons, i.e. 3 lone pairs. And again, this is an example where we don't actually have an octet here because the boron only has 6 valence electrons. If there are 4 pairs of electrons around the central atom, The furthest apart they can get is when they point to the four corners of a tetrahedral. And so this shape is called tetrahedral. And the bond angles between everything are 109.5 degrees, 109.5. Now this is a 3D arrangement, it's not a planar shape. So the linear was essentially a planar shape, the trigonal planar is a planar shape. And so our angles have to add up to being 360. However, if we've got a 3D arrangement where it's not planar, the sum of the angles can be greater than 360 degrees, which is what we have here. And so examples of this would be methane CH4 or the ammonium ion NH4+. Now notice that the charge doesn't affect the shape directly. It can still be tetrahedral even though it's an ion rather than a molecule. The only thing that is affected by the charge is the number of electrons. And of course, the important thing is to always count the number of electrons. And so if we look at the methane example, for example, the CH4, we have our central atom being the carbon. So we now have 4 valence electrons on our carbon. We can think of each hydrogen as donating 1 electron in these covalent bonds. It shares 1 electron with the carbon. And therefore, we have 4 electrons from the total of the hydrogens, 4 electrons from the carbon, that's 8 electrons, divide by 2, that's 4 electron pairs. So a tetrahedral shape with bond angles of 360 degrees. The ammonium ion, exactly the same. We have nitrogen, which has 5 electrons, it's in group 5. We have our 4 NH bonds, these covalent bonds, that's going to be 1 electron shared from each hydrogen, so in total 4 electrons from the hydrogens. That gives us 9 electrons, but we have to remember we have a positive charge on our ammonium ion. If we have a positive charge, that removes 1 electron. And so we go down to having 8 electrons, divide it by 2 because they're in pairs, that's 4 electron pairs, that tetrahedral shape. And so if we have an ion, if we have a positively charged ion, we have to remove an electron. Think about how it's become a positively charged ion, it must have lost an electron. And conversely, if you have a negatively charged ion, it must have gained an electron, and therefore you add an electron to your number. If there are 5 pairs of electrons, the shape is normally something called trigonal bipyramid or trigonal bipyramidal. Here we have bond angles of 90 and 120 degrees. And so a really typical example of this is phosphorus pentachloride, PCl5. And so we can think of our phosphorus as it being in group 5, same as nitrogen, so it has 5 valence electrons. Each chlorine is going to donate 1 electron, share 1 electron in these covalent bonds. And so therefore we have a total of 5 from the chlorines, 5 from the phosphorus, that's 10 electrons, divided by 2, that's 5 pairs of electrons, a trigonal bipyramid or a trigonal bipyramidal shape. And you can see here that we have a 90-degree angle. It's quite clearly being able to see there that 90-degree angle. But we also have 120 degrees as well between the chlorines that are shown using the dash and the wedged bonds. And remember that the wedge bond implies that it's coming out of the page towards you. The dash bond indicates that it's going into the page away from you. Now notice also how the phosphorus now has 10 valence electrons. So here we've actually again broken this octahedral that we think of, this stable noble gas configuration of 8 electrons. The reason it can do this and have 10 electrons is because phosphorus is in period 3. So if we think about the orbitals that we have available to us, let's think about the carbon or the nitrogen example above for tetrahedral. Carbon and nitrogen are in period 2. So if we think about the orbitals that they have available to them, it's the 2s and the 2p really that are our valence orbitals. We have 3 2p orbitals, we have 1 2s orbital, and therefore in total we have 4 orbitals, therefore we can accommodate 8 electrons. That's our octet rule. Because phosphorus is in period 3, we have the 3s orbitals, the 3p orbitals, but we also have the 3d orbitals being available. And so because we have these extra orbitals, and typically we have these orbitals that are actually of a fairly low enough energy that they can be populated, it means that we can actually exceed this 8 electron octet rule. It's something called hypervalence. So if you come across something like this where you have more than 8 electrons, it doesn't necessarily mean that it's actually wrong. If it's in period 2, for example carbon nitrogen, yes it would be, we don't have any extra orbitals to use, but period 3 and below we have extra orbitals we can use. So 4 pairs of electrons is tetrahedral, bond angle of 109.5. 5 pairs of electrons is trigonal bipyramidal with bond angles of 90 and 120 degrees. Now, if there are 6 pairs of electrons around the central atom, this shape is called octahedral. And the reason for that is that essentially, if this was a 3D shape, it points to the edges of an octahedron. And so it's an octahedral shape. And all of the bond angles are exactly 90 degrees. There's 90 degrees between every, in this case, the SF6, the sulfur hexafluoride. Every single bond angle between any of these fluorines is 90 degrees. Now note that an octahedron, the reason it's called an octahedron is it has 6 points but 8 faces. So it's a slight kind of, if you think why does 6 electron pairs give us an octahedron? It's because the 3D shape has 8 faces but 6 points. Another example is this iron hexaaqua ion, this iron complex ion. Again, exactly the same thing though. If we looked at the SF6, for example, sulfur is in group 6, therefore it has 6 valence electrons. Each fluorine is in group 7, so each fluorine is going to be using 1 electron to form covalent bonds, going to be sharing 1 electron with the sulfur. So we have a total of 6 electrons from our fluorines. Then we have the 6 that we had from our sulfur. That gives us 12 electrons in total, and therefore divide by 2, that gives us 6 electron pairs. The iron one is a bit more difficult to work out in terms of the actual electron configuration, but essentially what we have here is an iron atom with 6 bonds to water. And so essentially we have 6 electron pairs, 6 covalent bonds, we have 6 water molecules coordinated, and so therefore it must be an octahedral shape. And so the way to kind of visualize this kind of in 3D almost is that we have a square plane. We could draw a square between the water molecules that are with the dash and the wedged bonds. And then we have the one in sort of above and below going out of that square plane. Now, some molecules have lone pairs of electrons that aren't part of a covalent bond. And lone pairs affect the shape and the bond angles. We said earlier on that lone pair repulsions were greater than bonding pair repulsions. So lone pairs, we have to include them if we have them in our molecule in terms of counting electrons, but they also influence the bond angle as well. And sometimes it can be helpful to draw the dot and cross diagrams that we looked at back in the first video of this series to help identify lone pairs. So for example, let's take ammonia, NH3. We know that nitrogen is in group 5, so it has 5 electrons. We have 3 NH covalent bonds. The hydrogen is going to be using 1 electron to share in these covalent bonds. So we have 3 electrons from our hydrogens, 5 from the nitrogen. That gives us 8 electrons. Divide by 2 because they're in pairs. That gives us 4 pairs of electrons. And now it's really important to think about actually whether they're bonding pairs or they are lone pairs. So because we have 4 pairs of electrons, the shape is based on a tetrahedral. Remember that CH4 example earlier on, 4 pairs of electrons was a tetrahedral shape. So what it actually means, we call this the pseudostructure essentially, where we just literally work out how many pairs of electrons there are. Here there are 4 pairs of electrons, and so the pseudostructure, what it's based off, will be a tetrahedral structure, tetrahedron. However, there's only kind of 3 arms on this molecule. There's 3 bonding pairs. We have 3 NH bonds. That must mean we have one of these electron pairs being a lone pair. So one of those sites on the tetrahedron actually is now occupied by a lone pair. And the shape is actually called something different. It's called a trigonal pyramidal shape. And this is because essentially we have, if you just looked at where the hydrogens are, they map out a triangle. But because this isn't a planar molecule, essentially if you drew the shape for this, it would look like a pyramid with a triangular base. And so trigonal pyramidal, or a trigonal pyramid. And so the way to see this is that the electron pairs form a tetrahedron, but the bonds form a triangular pyramid. Now we said earlier that the angle for a perfect tetrahedron, the bond angles there, were 109.5 degrees. But actually in ammonia, the angle between each NH bond is roughly 107 degrees. And this is because the repulsion between lone pair and bonding pairs is greater than bonding pair and bonding pairs. Remember we talked about this when we talked about our VSEPR theory on the first slide. Lone pair repulsions are greater than bonding pair, and so lone pair bonding pair repulsions are greater than bonding pair bonding pair. And so what this has the effect of doing is the lone pair essentially squeezes the hydrogen atoms together. There's more repulsion at the top of the molecule, and so essentially it squeezes all these NH bonds slightly closer together. And so the angle has gone down from 109.5 down to 107. And generally, for any lone pair that we have, we reduce the angle by about 2–2.5 degrees. The next example to look at would be water. So if we take water, H2O, oxygen's in group 6, therefore it has 6 electrons. The hydrogens, again, are going to be using 1 electron in these covalent bonds, so they're going to be sharing 1 electron. So we have 2 electrons in total from our hydrogen, 6 from the oxygen, that's 8 in total, divide by 2, gives us 4 electron pairs. So again, we'd say that our pseudostructure, the shape that this is based off, is a tetrahedral structure, because we have 4 electron pairs. Again, though, we'd have to consider, are these bonding pairs or are these lone pairs? And very simply, we can think of the formula, H2O, therefore we have 2 oxygen-hydrogen bonds, and so 2 of those are bonding pairs, 2 of them are lone pairs. And so again, it was based off a tetrahedral structure, but now there are only 2 arms, there's 2 bonds in this molecule, and so this results in what we call a V-shaped, or an angular, or a bent molecule. And you can see there at the bottom that essentially we've still got a tetrahedral shape, it's just that now 2 of those sites are hydrogens, 2 of the sites are lone pairs. And again, now because we have 2 lone pairs, rather than just having 4 bonding pairs, remember that I said that the angle gets reduced by about 2–2.5 degrees. So starting off from the perfect tetrahedral structure of 109.5 degrees, we can reduce that by about 4 or 5 degrees. And you can see it goes down to 104.5 degrees, a loss of 5 degrees. And so our angle is 104.5 degrees. This is a V-shaped, an angular, or a bent molecule. Another molecule to look at would be chlorine tetrafluoride, ClF4-. If we count our electrons for this, chlorine here is our central atom. Chlorine's in group 7. Our central atom we have to count all the valence electrons for, so we have 7 electrons. Each of the fluorines is going to be using 1 electron in a covalent bond. It's going to be sharing 1 electron. So we're going to have a total of 4 electrons from our fluorine, 7 from the chlorine. That therefore gives us 11 electrons. But we have a negative charge. And remember, if we have a negative charge, it must have gained an electron. So we add an electron to our total. That is 12 electrons. And therefore, we divide by 2 and we get 6 electron pairs. Now remember that we said for 6 electron pairs, our shape was an octahedron. And therefore, we know that our pseudostructure, the shape that this is based off, will be an octahedral structure. However, again, we have to think about how many bonding pairs and lone pairs we have. We have 4 ClF bonds, and so therefore we must have 4 bonding pairs and 2 lone pairs. Now remember we said that lone pairs repel the most. They are the lone pair repulsions are the greatest, and so they're going to adopt positions that are furthest away from each other. And so they actually adopt positions that are 180 degrees away from each other. So going back to that octahedral type shape, we said that we had this kind of square plane in the middle, and then with something going above, something going below. Our lone pairs occupy these what we call the axial positions, where the fluorines occupy what we call the equatorial positions. And you can see that these positions kind of above and below, these axial positions, are occupied by lone pairs, 180 degrees apart. And what this actually leaves now is something called a square planar structure. By removing the 2 axial positions, we're just literally left with that square plane, a completely planar molecule in the shape of a square, so a square planar structure. And you can either draw this as a kind of, using the dash and the wedge bonds to sort of dictate that it's definitely a square with some going behind, some going in front, all in one plane, or you can just draw it out as a kind of, almost like a sort of T-shaped thing above, where we just use our normal covalent bonds. And so lone pairs will always occupy positions as far apart from each other as possible, because lone pair repulsions are greatest. And as I said on the previous slide, in general, each lone pair reduces the expected bond angle, that's the bond angle that we have for our pseudostructure, by about 2 or 2.5 degrees. So in summary, what we need to know is, first of all, how to calculate how many electron pairs are around our molecule. As I said, to do this, we have to consider what's the central atom, how many valence electrons does the central atom have. Then I prefer to use the sort of cheap way of working out how many electrons our other atoms then have by thinking about how many electrons they're going to be using in a covalent bond. So for things like hydrogen, fluorine, chlorine, it's 1. For stuff like oxygen, it's 2. Rather than considering all the valence electrons, just consider how many they're likely to donate, how many they're going to share in a covalent bond. We add all our electrons together, divide by 2, that gives us our number of electron pairs. That will give us what we call our pseudo structure. And we also have to consider how many of these are bonding pairs or how many of these are lone pairs. We also have to know, once we now have our shape of the molecule, we have to know what the shape actually looks like. So make sure we know how to draw out a tetrahedral, a trigonal pyramid structure, a bent structure, whatever these might be. Make sure you know how to draw them out correctly using dash and wedged bonds as well, because we have to show them in the 3D arrangement. We need to know the bond angles, and we also need to know what the name of the shape is. And so here I've just taken a load of different things, a load of different pictures and summary tables from online. But you can find lots of these online, and you can find one that will sort of match what you want, or even make one yourself. And I recommend just sticking one of these up in your bedroom or something, where you can look at it every day, and it just kind of you'll find over time that it will be absorbed into your head just by looking at this more and more. But really, practice makes perfect for doing these shapes. So, time to have a go at some questions. So here we have some molecules, and we're going to be looking at the names, the shape, and the bond angles for the following molecules. So, if you want to have a go, pause the video, and the answers will be on the next slide. So the first one here is carbon dichloride, CCl2. So carbon here is our central atom. We have 4 electrons on the carbon. Chlorines, we can either think of them as, here I've denoted it here as using all the electrons, so using all the valence electrons, so that's 7 for each chlorine, giving us 14 there, a total of 18 electrons, divide by 2, 9 electron pairs. The way that I don't really like using this way of talking about it is because the 9 electron pairs isn't particularly helpful in depicting what the shape is. So I always recommend doing it by using just the how many electrons are going to be shared in a bond. So the chlorines will share 1 electron each, therefore we have 2 from the chlorines, we have 4 from the carbon, so that's 6, divided by 2 gives us 3 electron pairs. We then have to think about, are these bonding pairs or lone pairs? We have CCl2, so we must have 2 bonding pairs and 1 lone pair. So our pseudo structure, the shape it's based off, has 3 electron pairs. That's a trigonal planar structure. Bond angle in a trigonal planar structure is 120 degrees. But because we have this lone pair, essentially it ends up becoming something that looks a bit like a water molecule. It has this bent structure, or a V-shaped or an angular structure. And remember that our trigonal planar had a bond angle of 120 degrees. Each lone pair reduces it by about 2.5 degrees, and so our angle here would be roughly 118 degrees. Question B was BCl3, boron trichloride. The boron has 3 electrons, being in group 3. Again, we can use the chlorine as having 7 electrons, or I'm going to do it here using just the 1 electron it would donate. So we have 1 each from the chlorine, that's 3 of them. 3 from the boron, that gives us 6 electron pairs. 6 electrons divided by 2 gives us 3 electron pairs. Therefore, we have 3 bonding pairs because we have BCl3, 3 boron-chlorine bonds. Therefore, we have 3 bonding pairs, 0 lone pairs, and so our shape is just trigonal planar, and it's 120 degrees, the bond angle. Question C, nitrogen trichloride, NCl3. Now, a common mistake here is if you don't count up your electrons to think that NCl3 looks exactly the same as BCl3, because we have 3 bonding pairs. The key thing to note is, of course, nitrogen has a lone pair. And so we have to work this out properly. So our nitrogen has 5 electrons from being in group 5. Each chlorine will donate 1 electron in a covalent bond. It will share 1 electron. And so therefore we have 3 from our chlorines, 5 from the nitrogen, that's 8 electrons, divide by 2, that comes out to be 4 electron pairs. So our pseudostructure, the shape it's based off, is tetrahedral. We know that has a bond angle of 109.5. Here though we have 3 bonding pairs and 1 lone pair. Remember, our lone pair will sort of squish the NCl bonds a bit closer together because the lone pair repels more. And so therefore we have a bond angle of about 107 degrees and the shape is trigonal pyramidal. Question D, xenon tetrafluoride, XeF4. Xenon is a noble gas, so it's in group 8, it has 8 valence electrons. Each fluorine is using the 4 unpaired electrons, so here I'm not going to bother doing it in the total valence electrons, just to do it in the 4 that it would donate. If you do the using the total valence electrons of everything, the easiest way I would say to do it is to draw out a dot and cross diagram first, like I've been doing on the left of each example, and then actually drawing out the shape after that once you've worked out how many electron pairs are around your central atom. But if we're doing it just using how many electrons it would share in a covalent bond, quite often we can go straight to the shape. So we have 4 fluorines, each that will donate 1 electron, 8 from our xenon, that gives us 12 electrons, divided by 2 gives us 6 electron pairs around our central atom. We then have to think about bonding pairs and lone pairs, so we have 4 xenon-fluorine bonds, so that's 4 bonding pairs and 2 lone pairs. Remember, our lone pair repulsions are the greatest, they're greater than lone pair bonding pair and greater than bonding pair. So our lone pairs want to go literally as far away from each other as possible. And so they go 180 degrees away from each other in these axial positions of the octahedral pseudostructure. And what we're left with is a square planar structure with bond angles of 90 degrees. E, phosphorus pentachloride, PCl5. Phosphorus is in group 5, so 5 electrons. Chlorine is each going to donate 1 electron in a covalent bond, and therefore 5 in total. 10 electrons divided by 2 is 5 electron pairs. We've got PCl5 from 5 electron pairs, so it must be 5 bonding pairs and 0 lone pairs. And so therefore we end up with a trigonal bipyramidal structure and bond angles of 90 and 120. Remember, there's 2 bond angles in the trigonal bipyramidal structure. And then finally, F, PCl4+. So our phosphorus here is in group 5, so we have 5 electrons from it. Each chlorine is going to donate 1 electron in a covalent bond, so that's 4 electrons from the chlorines. That gives us 9 electrons, but the key thing is it's an ion. Remember, if we have an ion, a positive charge takes an electron away, a negative charge adds an electron. We have a positive charge, so we take 1 away. That gives us 8 electrons, divided by 2. That's 4 pairs of electrons, so the pseudostructure is tetrahedral. We then look for bonding pairs and lone pairs. We have PCl4, 4 bonding pairs therefore, and 0 lone pairs. And so we do end up with a tetrahedral structure with angles of 109.5. So generally for these kind of questions, always work out how many valence electrons are around my central atom. I then recommend using the method of how many electrons are being donated in this covalent bond from the other atoms. Work out the total number of electron pairs around the central atom. That will give you the pseudostructure. Look to see how many bonding pairs and lone pairs you have. That will give you the real structure, and then draw it out properly using dashes and wedges if necessary, and give the bond angle. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check out my tuition pages if you're interested. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.